Hello and welcome to this video on manifolds. Let's start with the temperature of the surface of the earth, which is simply a map T to the real numbers R. We had surely want this map to be smooth, but what could smoothness mean in this case? In fact, what could smoothness mean for any map from some kind of object to another? In mathematics, maps and space are bound together tightly. For example, a linear map preserves a linear structure of vector space. A group homomorphism preserves the group structures. What could this mean in our case? Which kind of structure do the earth or other objects need or smooth maps to be defined? Okay, so you see that I have written this I am writing this map and space. Okay, so first of all, remember that differentiation involves taking limits, and every smooth map is certainly continuous. For this concept to make sense, we need a notion of open sets on our space. This is provided by calling our space topological. So continuous map is topological, so if inverse is open. So furthermore, these limits out to be unique, and so we require any 2 points of our space to be separated by two non-interfering open sets. This property is called Hausdorff. With this at hand, we can go back to the temperature of the earth and find out which kind of structure smoothness requires. Now here comes the crucial observation. If we zoom in and look the temperature locally, okay, we find an ordinary map from some subset of r square, which is given by gray axis onto the real numbers given by the red axis. Okay, red axis, but this kind of map we surely know that smoothness means. Okay, how can we express the zoom procedure mathematically? Our local set, let call u1. u1 I have already drawn. u1 is homeomorphic to a subset v1 in r square. This is there exists a continuous map phi 1, phi 1 from u1 to v1 with a continuous inverse. This map is called coordinate function. So what we actually considered when we zoomed in was the composite map T after phi 1 inverse, for which we surely know what smoothness means. Going back, we just zoomed in here, and but we can also zoom in here or anywhere, and find a map r square to r in the end, and we have covered the whole surface with sets and got an atlas of the earth. There may be two or more charts covering the same area of the earth. In case we require the transition maps and coordinate transforms phi beta after phi alpha inverse to be smooth. Now we are ready to give the full definition of manifold. Okay, phi b and phi inverse. So now we discuss the definition of manifold. A topological space M is called a d-dimensional smooth manifold if it is Hausdorff, it is second countable, it comes with a family U alpha and psi alpha with sets U alpha is open capital M and homeomorphism psi alpha such that U alpha tends to R to the power D, and R superscript D, not power, such that M union U alpha. So we given that U alpha intersection U beta does not equals to phi, and map phi beta composed phi b inverse is smooth, and phi alpha a coordinate function, alpha a coordinate function. So the pair U alpha and phi alpha are called charts. The whole family atlas, the phi is coordinate function. Phi alpha is a coordinate function. So remark is that you might have noticed that we required our space to be second countable. This makes every connected component of our space in a certain sense compact and ensures that integration will be well defined. Okay, so what about our map F between these two-dimensional manifolds? So it is second countable means paracompact, and integrations will be well defined. So we want it to be smooth no matter which kind of local coordinates we choose. So we say it is smooth, and psi b after f psi alpha inverse is smooth for alpha and beta. Okay. So we need to remember that continuous is continuous map, and smooth is the subset of the continuous map. So psi b after f and psi alpha inverse is smooth for alpha and beta. So we see that psi b vb is the subset of r square, and psi u alpha subset of r square. So if you had like to dig a little bit deeper into this topic, take a look at the books by Spivak and Nakhara, or any other differential geometry or topology book. So whatever we get psi b composed psi alpha inverse. Okay,